Hello everyone, and welcome you all in the problem solving class of the course Applied Electromagnetics for Engineers. I am Vivek Kumar Srivastava, a PMRF research scholar of Antenna and Microwave Research Laboratory, EE Department, IIT Ropar. So, in some of our previous classes, we have seen problems based on the topic lossless as well as lossy transmission line. Then we have seen numericals based on the topic impedance matching network, where we have seen some of the graphical tools that we can use for impedance matching network designing, basically the Smith chart. Okay, so on the basis of that, we have seen some other techniques, that is quarter wave transmission for impedance matching network. Okay, and then we have seen L section matching network and stub matching network. Okay, so in the today's class we will mainly focus on the topic, that is transient analysis in a transmission line. So let's start the presentation. Okay, so here is the first problem. Okay, a 50 ohm transmission line of length 60 meter is terminated by a 150 ohm load. Okay, so let us suppose this is a 50 ohm transmission line. Okay, having a length of 60 meter. Okay, and this is terminated by a load of impedance ZL is equal to 150 ohm. So at the source end, suppose this is a source. Okay, so a rectangular pulse has been applied. Okay, a rectangular pulse of width 5 microseconds. So the width of this rectangular pulse is 5 microsecond is applied, and having a magnitude, or say amplitude, is this amplitude is 4 volt. Okay, is sent out by the generator connected to the line. Take Zg is equal to 25 ohm. So here is the Zg, which is equals to 25 ohm, and the velocity of the wave is v is equal to 0.1 c, where c is the speed of the light. So we have to determine what is the initial current that is flowing through the transmission line. Okay, so any idea that how to proceed in this question? Praveen and Anshuka. Okay, yes, yes, please. Praveen, are you saying something? I'm asking that how to proceed. Can you please tell me that how to solve this question? Any idea? Okay, 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 no problem. So see, so if suppose this is a transmission line and this source is now connected to this transmission line, so what happens? There will not be any reflection. Okay, when this source is connected to this transmission line. Okay, so at in this case, the impedance seen here at the input terminal of this transmission line will be equals to 50 ohm. Okay, so the initial current that has been flowing through this transmission line is given as I naught, let us say, is equals to 4 volt divided by 25, which is the impedance of the generator itself, plus 50 ohm. Okay, so this is the characteristic impedance of the transmission line, which is seen by the source when there is no reflection, means when this source is connected to the transmission line. Okay, so that's how you can calculate the value of initial current. So uh, it is obtained as 53.33 milliampere. So any problem in this question? Any doubt? Okay. So our second question is related to the first question. So in the first question we have obtained that what is the value of initial current that is flowing through the transmission line when the generator is connected to the line. So in the second question we have to determine the value of initial voltage. Okay, uh, that is obtained by this transmission line. Okay, so any idea? Yes, but R is what is the value of R here? 150 ohm load. So like here you are saying, na? See here, once this uh, generator is connected to the line, okay. So I am talking about the initial voltage. Means here now only we have connected the source. Okay. So the voltage or current will flow through this line without any reflection. Okay, so in that case the impedance seen by this source is same as the impedance of the transmission line. It will not uh, equals to 150 ohm, it will be equals to 50 ohm only. Okay, so initial voltage V naught is equals to I naught into Z naught. So I naught we have already calculated. It is equals to 53.33 milliampere, and the impedance of the transmission line it is given as 50 ohm. So the initial value of voltage that is obtained at the transmission line terminal is 2.67 volt. Okay, any doubt? Okay. So the third question is determine the current reflection coefficients. Okay, so if suppose here is the load is connected, uh, having a value of 150 volt 150 ohm, with a transmission line of characteristic impedance of 50 ohm. Similarly the source impedance is given as 25 ohm. Okay, so at both the uh, receiver in means at the load terminal as well as at the input side of the transmission line, in both of these 2 points reflection will occur. Okay, so we have to find out the value of reflection coefficient both at the load side as well as source side. So how to determine the value of reflection coefficients? Okay, so basically, if suppose this is the transmission line having impedance of Z naught, okay, and here a load is connected having a value of ZL, and here is the source impedance ZG, let us suppose, and here is the source. Okay, so at the load side, the reflection coefficient ZL, sorry, gamma L is defined as ZL minus Z naught over ZL plus Z naught. Okay, so ZL value is already given. It is equals to 150 minus 50 over 150 plus 50. So we can calculate this value. It is 1 by 2. Okay, similarly at the source side also we can calculate the value of reflection coefficient. It is equals to Yeah, it is equals to, sorry, 25 minus 50 over 25 plus 50. So the value of reflection coefficient at the source side is minus 1 by 3. Okay, so that's how you can calculate the reflection coefficient at both the load side as well as source side. So next question is, in the question 1, find out the generator in total current for the time duration of 4 to 5 microsecond. Okay, so see, in our previous question we have find out the value of initial current is defined as 53.33 milliampere. Okay, so for solving this question we have to basically draw a lattice diagram. Okay, so here I am drawing the lattice diagram. So here it is defined as z and here is the time t. Okay, so see, once you applied the source to the transmission line, it will take certain time to reach at the load terminal. Okay, so this time instant is defined as t is equals to the length of the transmission line divided by the velocity of the wave. Okay, so this time taken by the wave to reach at the uh, load terminal is defined as transit time. It is equals to t is equals to L by u. Okay, so L is already given in the question, it is 60. Okay, and u is also given there, which is equals to 0.1 times c. Okay, so that's how you can calculate the transit time, which is equals to 2 microsecond. So this 2 microsecond time has been taken by the wave to travel to the uh, load terminal. Okay, so after that, uh, here reflection will be occur, some part of wave will be reflected here. Okay, so it will take another t time to reach here at the load terminal, oh sorry, source terminal. Okay, so here gamma g, sorry, here it will take another t time to reach to the source terminal. Okay, then after a reflection has been occur from the source side. Okay, so here due to the reflection from the source side some signal will be flow. So that's how the signal will be flow through the transmission line. Okay, so the total transit time that has been taken by the wave to reach at the source side is given as 2t1, which is equals to 4 microsecond. And also one more thing that we have to see, like here in the question it is given that the pulse width of the uh, rectangular pulse is 5 microsecond. It means that it means that ki here at 4 second also some wave will be reflected from both the load as well as source side, but till 5 microsecond the source will supply some current to the transmission line also. Okay, so here the till this point the source will supply this much amount of current. Okay, so let us now find out the value of current that is flowing through the transmission line. So initially the current flowing through the transmission line is 53.33 milliampere. Okay, after reaching to the load terminal at time 2 microsecond, some reflection will be occur from the load towards source. Okay, so this reflected current you can find out by multiplying the total input current with the load reflection coefficient. Okay, so here is the load reflection coefficient. So you can multiply this initial current with the load reflection coefficient, and you will find that this much amount of current, that is 26.665 milliampere, will be reflected from the load towards the source. After reaching here, that is up to 4 seconds, another reflection will be occur from source toward load. Okay, so this reflected current has been found out by this gamma L I naught, and this will be gamma G into gamma L into I naught. Okay, so that's how you can find out the reflection from the source side, reflection current from the source side. So the total current that is flowing between the interval 4 microsecond till 5 microsecond is obtained by the sum of these three currents, that is this current plus this current plus this current. Okay, so you have to sum all these currents, then only you can find the total current that is flowing through the transmission line from 4 microsecond till 5 microsecond. Any doubt in this question? Okay, so in question 5, we have to find out the total current at the generator side for uh, the time interval of 9 microsecond to 12 microsecond. Okay, so here we will draw the bounce diagram again. Okay, so we have seen that uh, after 4 microsecond, reflection will reach at the source side. Okay, until 5 microsecond the source will supply the current of 53.33 microsecond milliampere. Okay, yeah, 53.33 milliampere. So this will be the initial current. Okay, till 5 microsecond the source will apply this current. Okay, after that, the as you know that this is a pulse. Okay, so after that the current supplied by the source will be 0. Okay, so this will be 6 microsecond, then this is 8 microsecond, then this is 10 microsecond, and this is 12 and 14 microsecond. So we have to determine the value of current between 9 to 13 interval, means in this interval how much current is flowing through the generator end, we have to find out. Okay, so here between so first of all we have to determine the value of reflected current, that how much reflected current will be there. So like here, uh, till here we have already find out the value of reflection current, which is equals to minus 8.889 milliampere. So here the value of current will be minus 8.889 milliampere. Okay, so after that we will again find the value of reflected current through the load. Okay, so this is obtained as uh, reflect reflection coefficient through the load, which is equals to this into the incident current, which is equals to this much. Okay, so the total current that is reflected from the source between the interval 6 to 8 microsecond is obtained as 4.445 milliampere. After that, once the this wave will reach toward the source side, again reflection will be occur from the source side. Okay, so this you can obtain as 1 by 3 into 4.445 milliampere. So this much current is obtained, that is reflected from the source side. So the total current that is that is flowing through this source side between this interval is obtained as sum of the current, means these two currents, which is reflected through the load and then it is reflected through the source. So the total current in this here is obtained as the sum of these two. So that's how you can calculate the total current between the interval 9 to 12. So if suppose here I am not uh, given the uh, current that is reflected from between this interval, that is 12 to 13 microsecond, so you can obtain by the similar way. Okay, so any doubt in this question? So this is a question for you. Okay, so the question is, lattice diagram shows option A, the position at any instant of incidence, reflected and transmitted current or voltage surge. Option B, the direction of motion at any instant of incident, reflected and transmitted current or voltage surge. Option C, both A and B, and option D, none. So any idea that which option is right here? Option D. Okay, option B. And Jay Prakash, B only. Why not option A? Because see, the lattice diagram is also known as space-time diagram. Okay, it is a space-time diagram. So whenever you draw a lattice diagram, so here we will specify the uh, space and here we will specify the time. So the position at any instant of incident, like incident angle, where is the incident, sorry, where is the incident wave, where is the reflected wave, how much is the transmitted wave. Okay, so here also we have defined the wave in term of position as well. Okay, so option A is also correct here. Option B is correct only, but here option A is also correct. So the correct answer is option C. Any doubt? So the next question is, which one is correct? Option A, in a lattice diagram, the horizontal axis represents the time taken to travel. B, in a lattice diagram, the vertical axis represents the distance traveled along the system. Option C, both A as well as B. Option D, none of these. So, Praveen and Jayaprakash, any idea? Which one is correct here? Option A. And what's about Praveen? So, like, Option B. Okay. Praveen says option B and Jayaprakash option A. Okay, so like here only I draw one lattice diagram. So here the horizontal axis represent the space, means position, and the vertical axis represent the time. So according to this, the horizontal axis, it is it says that time taken to travel, means this option is wrong, because in vertical only we will represent the time. In horizontal we represent the space, that is position. Okay, so none of these is, option D is correct. So the next question is, which one is the type of system transient? A. Surge phenomena, B. Short circuit phenomena, C. Transient stability, and option D. All of these. So which one is correct? Okay, so basically here the correct answer is all of these, because surge, if suppose uh, this is a transmission line, no, so this is connected to a load. So if suppose here is the source, here I am connecting one uh, switch. Okay, so once this switch will be closed, then there is a chance of transient. Okay, so initial what happen here, the once you close this switch, okay, so it will take certain time to reach the source voltage to the load. Okay, so some transient phenomena will be occur. Okay, similarly if suppose at the load side, this load side, some short circuit will happen. Okay, so this also create a lot reflection. Okay, reflection is defined as -1. So see, the whole voltage which you are uh, supplied to the source, to this transmission line, all of this voltage will be reflected towards the uh, source side only. So this will also create a uh, transient, or say transient performance. Okay, similarly if suppose some surge phenomena will be occur, then also this will create transient phenomenon. Okay, so option D is correct only here. Any doubt? Okay, so the next question is, plot the bounce diagram for the transient circuit shown in the accompanying figure. So sorry, here I think here is the figure. Here is the figure. This one include at least three reflections. Okay, so we have to consider at least three reflection here, and also we have to determine what is the total voltage at the midpoint of the line. That is, if suppose this is the transmission line having length of L. Okay, so in between this transmission line, that is L by 2, we have to find out the value of total voltage here. Okay, and also the time is given as uh, 3L by Vp. Okay, so for solving this question, we have to first uh, find out the value of initial voltage that is obtained at this transmission line when this switch is closed. Okay, so for finding out the value of initial voltage, what we will do, as we have done is the problem one, we have to take the So there we have calculated the initial current. So here we are trying to find out the value of initial voltage that is flowing through this transmission line. Okay, so the input voltage is given as 10 volt. Okay, so this 10 volt is basically distributed uh, in between this source impedance and the input impedance of this transmission line, which is equals to 50 ohm. Okay, so the input current initial value of voltage that is flowing through this transmission line is calculated as 10 into 50, which is the uh, impedance of seen by this transmission line, divided by 50 plus 25. Okay, basically this is a voltage division rule. Okay, so that's you have to apply for finding out the value of initial voltage that is flowing through this transmission line. So this uh, voltage will travel to this transmission and through this transmission line and reach to the load at some interval of time. Okay, so if suppose the length of this transmission line is L, and uh, velocity of wave that is travel through this transmission line is V, so the time taken here will be this will be L by V. Okay, so this much time of transient time it will take to uh, reach the initial voltage to the load. Okay, so after that the load will see some reflection. Okay, so this wave will see some reflection from the load side. So for finding out the reflected voltage, we have to first determine the value of reflection coefficient at the load. So this we can determine as ZL minus Z naught divided by ZL plus Z naught, 100 plus 50. So this will be equals to 1 by 3. Okay, so you have to multiply this ZL in by 6.67, means this initial voltage. So the voltage that will be reflected, yeah, so the voltage that will be reflected through this transmission line from the load side is obtained as 2.22. Okay, so this will be the first reflection. Okay, after that it will take another L by V time to reach at the source side. Okay, so here also some reflection will be there because this source impedance is not equals to the load impedance. So reflection we can calculate, it will be equals to minus 1 by 3 basically. Okay, so once you calculate the value of uh, reflection coefficient at the source side, so you have to multiply this reflection coefficient by 2.22. So the reflected voltage from the source side is obtained as minus 0.74 volt. Okay, so this is the second reflection, and this reflected voltage will reach to the load after another L by V. Okay, after another L by V it will reach to the load. Okay, so then also some reflection will be occur because the load impedance is not matched to the impedance of the transmission line, or the characteristic impedance of the transmission line. So you have to basically multiply the incident voltage, uh, the second incident voltage due to this reflection, okay, into this load reflection coefficient. So the reflected voltage from the load side is obtained as minus 0.246 volt. Okay, so we have considered all the three reflections which is given in the question. So here in the question only it is given that we have to consider at least three reflections. Okay, so we have considered the three reflections. So in the question also it is given that we have to determine the total voltage at the midpoint of the line, means here we have to determine, and time it is given as 3L by Vp. So L by Vp is this much, another L by Vp is this much, then L by Vp is this much. So at this position and this time we have to find out the value of total voltage. So this total voltage is basically the sum of these three voltages here. Okay, so by summing all these three voltages you can determine the value of total voltage uh, at the midpoint of the transmission line at time t is equals to 3L by Vp. Okay, so that's how you can determine the value of total voltage. So any doubt in this question, Praveen and Jayaprakash? Okay, so the next question is plot the voltage at the midpoint of the transmission line in the previous question. So in the previous question we have basically draw the bounce diagram. Okay, so on the basis of that we have to determine the value of sorry, we have to plot the voltage at the midpoint of the transmission line basically. Okay, so for plotting the voltage, okay, we have to uh, first see the bounce diagram only. So like here in the bounce diagram it is given that if suppose this is the midpoint of the transmission line, z is equals to L by 2. So here we have to draw the uh, voltage. Okay, voltage profile we have to see. So till this point how much voltage that has been obtained at the uh, transmission line is given as 6.67 volt. Okay, so till this point the voltage will remains as 6.67 and the value, okay, this will be 1.5 L. till this till this point the value will remain same. Okay, after that here you have to add this reflected voltage as well. So the you have after adding this reflected voltage here, I have written it wrong. So you have to basically sum this voltages 6.67 plus 2.22. Okay, so this much voltage you will obtain at the midpoint of the transmission line. This is just because the reflection that has been obtained. Okay, so after another L by Vp. Okay, so another L by Vp, you you will see some decrement of the total input voltage by a factor of uh, minus 0.74. So you have to subtract this 6.67 plus 2.22 minus 0.74. Okay, so this much is the level of voltage or say amplitude. Okay, so here the value of voltage that you will obtain is defined as this much. So after another L by Vp, you have to subtract this much voltage from this voltage level. Okay, so that's how you can plot the voltage at any point at the transmission line. So any doubt? Sorry, your voice is not clear. Okay, 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 okay. So that's all for the today's class. Thanks all.